something that you probably already know pretty intuitively already, and that is that you can take a derivative, but then you could also take the derivative of a derivative, and then a derivative of a derivative of a derivative. Right? So it's really not just a question of the mechanics of it, it's also a question of the interpretation. All right. So we're familiar with the primes. You might not be familiar with what happens after you get the third derivative. So when you get to the fourth derivative, we represent it, instead of using primes, we represent it as kind of like a power, but in parentheses. The idea being that if you write it as like y with a power of 4, it could be confused as y to the fourth. So we put it in parentheses. Right? But you could also do the same thing with function notation. The reason why we need to know both is because we're not always going to be working with functions. All right. So dy dx, that's something we've seen a lot of. The second derivative, you'll notice that the power comes after the d, but it comes after on top, but it comes after the x on the bottom. All right. So what that's saying, and I'll just kind of make a notation of this, and this is very important because this is going to kind of give you a sense of the units of a function and its derivative. So this is the second derivative of y. Per change in x, per change in x. All right. So we've seen a case related to this already when we did the basketball project, when we talk about acceleration, right? Anytime we talk about velocity and acceleration, actually even before then, the second derivative was talking about the acceleration function, right? And the units for that were feet, which were the units of the y function, per second squared, all right? Units of x, or t in that case, were seconds, but it was squared. All right, so the notation for the second derivative tells us what the notation for our units should be. All right, so it's very, very convenient, but also, I'll say mandatory because, you have to use it. But what people have kind of been confused about in the past is, why is the power of 2 there for the d on the top and not there for the d on the bottom? And that's really just the nature of the situation. I'm taking the second derivative of y. All right, y is still the original function. It's just a rate of change in x in terms of x twice. All right, so that's what our second derivative is really talking about, and you can kind of expand that out to the third derivative, fourth derivative, and so on. Contextually, it gets more and more complicated to understand what each of these higher order derivatives are talking about. But if you always have it in mind that you're just incorporating another unit of perhaps time, then it gets a little easier, right? So if I were to say the third derivative, what I'd be talking about is the rate of change of the second derivative. Now, if the second derivative is acceleration, I'm saying how fast acceleration is changing, all right? The rate of change of acceleration, or the change in acceleration per unit of time, all right? And then if I talk about the third derivative, which is known as jerk, then I could say the fourth derivative is the rate of change of jerk, all right? So how fast jerk is changing, all right? So how fast one is becoming a jerk or not becoming a jerk if it's declining, So like maybe you were a jerk and now you're becoming less of a jerk, all right? So you could think of it that way. Right? No, that's not even remotely true. But yeah, we're all nice people in here. Cool. So anyway, the questions here are pretty straightforward. If it's just mechanically finding a derivative and finding a second derivative, it's just okay. I got f of x. I'd rewrite it as 12x to the 1/3 power. Then I would take the derivative of that, which would be f prime of x. So I just want to be flexible with the notation because I want to represent my answer in the notation that the question is presented in, right? So it would not be appropriate, even though you might not see why, it wouldn't be appropriate to change the notation on the fly. So if I'm asking you to find the derivative of f of x, I want you to write it as f prime of x. So don't switch it over to dy dx. All right. Later on in the course, we'll see many examples of why that's important. All right. So anyway, what's my first derivative?
4x to the negative 2/3.
4x to the negative 2/3. All right. So then all I need is my second derivative, so f double prime of x. So just do it again based off of our answer for the first derivative, which would be what?
Negative 8/3
Times x to the
Negative 5/3.
negative 5/3. All right. Now, the second question says find the second derivative of a trig function, which, you look at that. Well, is polynomial. Well, in this case, it was a radical function, but polynomial functions, they have kind of a set routine. It's pretty easy to kind of see where it's going. Trig functions you might think of as more challenging, but they're actually really not that bad. All right. Derivative of sine is what? Cosine. So 4 cosine of t. Derivative of cosine is negative sine. So plus 5 sine of t. And then I need my second derivative. So we know cosine has a derivative that's negative sine. So negative 4 sine t plus 5 cosine t. All right. It's just oscillating back and forth between sines and cosines. All right. So it's actually pretty easy to do it on the fly. But then you get to a seemingly impossible question like find the 99th derivative of the sine function. Well, it's not impossible because there's a cycle involved, right? So k of x being equal to sine of x has a derivative k prime of x, which is what? Cosine x. K double prime, which is negative sine of x. K triple prime, negative cosine of x. K quadruple prime, no, k to the 4th power with parentheses around it, which would be sine of x. All right, so it's a 4-term cycle. So I have my 0th derivative, my first, second, third, and fourth. I just need the 99th. All right, well, if everything's happening in 4-unit cycles, then I already know what my 100th derivative would be, because that's a multiple of 4. My 100th derivative would be what? Sine of x. So we just dial it back 1 from there. Negative cosine of x, exactum mundo. Very good. All right. This relationship typically only works with sines and cosines because, like for example, tangent has a derivative of secant squared. The derivative of secant squared, I promise you, is not tangent or any variation of tangent. Right? It gets more and more complicated. Right? But starting with a sine and going to a cosine, or starting with a cosine and going to a sine, is not complicated. So it's pretty straightforward. So anyway, I wanted to kick over to Desmos and just show you a visual representation. What happens when you have a function within a function? This is really the last major concept. Right? If you can get a handle on chain rule, then you're going to be pretty much good to go for anything else I could throw your way. Because all we're going to be doing from here on out is exploring different types of functions and how to find their derivative using these concepts. All right? So a function within a function, one thing that you could do is you can decompose the two functions, because what we're really dealing with here, if I had these two functions put together, I could be looking at, so if they were put together, we would have y of x is equal to 2x cubed plus 1 I'm sorry, 2x squared plus 1 cubed. All right, so that's what the function would be if I just took my u and replaced the u in the y equation. All right. So that's ultimately what we're trying to find the derivative of. All right, but the chain rule is basically telling us to take the derivative of each of those two components separately, what we call the outer function and the inner function. All right, the outer function is what is being substituted into, and the inner function is what is being plugged into that outer function. All right, so all you'd have to do is find the derivative of y, which is u cubed. Y is equal to u cubed. Its derivative dy du would be what? 3u to the second. All right, and then we also want to find the derivative of u with respect to x, because its independent variable is x, so du dx would be what? 4x. All right, so we have those two components. Dy dx can be found, and this is why the notation is so important. If I just take dy du and multiply it by du dx, what happens? Du's cancel. And you get dy over dx. Okay, so what we're going to do is we're going to take our dy du, which is 3u squared, and multiply it by du dx, which is 4x. All right, now that's not our final answer because my derivative dy dx should be in terms exclusively of x. So what should my next move be? Well, I want to get rid of the u. So how can I get rid of that u?
Plug in the equation for it.
Plug in the equation for it. The expression for u is what? 2x squared plus 1. Okay, so what we found here is the derivative of this original function, which we can't see because I've blocked it out. The original function, 2x squared plus 1. All right, so what we did was we actually took the derivative of this by really just kind of pretending that 2x squared plus 1 wasn't there at all. Like just some, kind of blurred out, but just some function being raised to the third power. All right, if I had something raised to the third power using the power rule, what would its derivative be?
Oh, it would be 3 times that.
3 times that something to the second power. And that's what that is. But the additional step is we also have to multiply by the derivative of the thing that's inside. All right, so we pretend that this function isn't there, take the derivative of it, so something to the third power becomes 3 something squared multiplied by the derivative of the something. That's the shorter way of doing it. But you can do it this way just by decomposing the function. In this case, it's very easy to do that because they already decomposed it for you. But if a function was just given to you as, let's say, for example, y is equal to the sine of x squared, and I have to take the derivative of that, I could write it as y is equal to the sine of u, where u is equal to x squared. All right, so decompose it into 2 separate functions. Take the derivative of each piece. dy du is what? Cosine u. Du dx is what? 2x. So dy dx would be the product of these two things. All right, cosine u times 2x, and then all I'd have to do is swap out the u for what it really is, which is x squared. But think about what I did here and how we didn't really have to do any of this. All right? Pretend the x squared isn't there. I have the sine of something. Derivative of sine of something is what? Cosine of that something times the derivative of the thing that's on the inside. Derivative of x squared is equal to 2x. All right? So just a quick one. Let's say I have y is equal to I'll keep it very simple, tangent of 2x, something relatively simple. And I just want to go right to the derivative, dy dx. Tangent of something has a derivative of what? Secant squared of that something, right? Now that something happens to be 2x. I just need to then multiply by the derivative of that something, which is 2. And that's really it, all right? So I'm only asking you to go through page 10, but I do suggest that you at least give number 2 on page 11 a shot, all right? It's pretty basic. It's along the lines of number 1. So I'll leave